All right, so there's actually a cool trick to all of this, and it's having to do with a little bit of trig. So if I pick a nice color here, you'll notice that you want your circle to be tangent here, right? To whatever you had before. So what you can do is, you know that this tangent line is going to look like this, right? Blah, blah, blah. I already know this, right? Oh, my circle. There we go. Hold up. There we go. So you have your tangent line, and that's obvious, right? So what you can do is recognize that you don't really need to find your derivative of your circle here. All you need is to know how much you need to move it relative to this point. The problem is, though, you don't really know how much this distance is. I mean, you know it's the radius, right? But it's like, you can't translate your circle based on your radius. I mean, you technically can, but I don't know. You can try doing it solely on that base, and it won't work. You have to do a little bit more drawn out, which is what I'm going to show you. So, you can just ignore everything I just said. It's just dumb blabber. But point is that if you will recognize that any circle, big or small, similar to like similar triangles, right? Like 30, 60, 90, these will all have this like the same, like you can do side length A over B, side length CD, like AB is equal to CD, right? Like that. It's the same thing for circles. So therefore, like proportionally to their radius, their slope should be the same at each point, right? So that's kind of like what the basis of this is. So if you recognize that this tangent line has to be perpendicular to the radius, right? Well, you'll also notice that in looking at the grander scheme of things, this thing will also be perpendicular over here, right? And eventually it'll cross your x-axis. So if we start with our circle, like if you type into Desmos r squared, or I think it's just r, like if you just write your basic circle equation, x minus n squared plus x minus y, or y minus another number squared is equal to your r squared, like that's your basic circle equation. That'll be at the origin, right? That's a circle, by the way. And you'll notice that like moving these is what moves it left and right and up and down, right? So I can just pick my radius, right? And that won't matter. I'm gonna just keep it as r for simplicity right now. I mean, not for simplicity, for like to keep it same for everything, so you can apply it to whatever you want. So knowing that, I know that I just need to move my origin such distance like this, and I need to move it up this distance, right? And if I do that, well, I know that like I can do trig to find this point given a radius of how much I need to move it. It's really hard for me to explain. I don't really know how to explain it directly in words, which is why I'm drawing it out. But as I go, you might catch along what I'm saying. So I'm going to do this. I'm going to call this blue length r for my radius, because it's going to be important later on. And I'm going to call this height right here. This is my height, right? If it'll connect. There we go. That's my height. And you'll also notice that we have a little other triangle here, right? You can kind of just draw these things out based on just, hey, look, it's possible to draw it. So you'll also notice you can draw another triangle right here. How convenient, right? So this may not mean a lot, but if you start recognizing that, hey, at this point, you know your x. You know where you want to connect it, right? So I can call this x comma f of x, right? That's like my y connection. And I think it'll be easier. Actually, I'm gonna just call it f of x for now, because when I relate back to the equation of the circle, there's gonna be a y in there. So if I call this x comma y, it's just gonna be confusing. So that's just x comma f of x. So you'll realize I need to move this circle this distance, x. So I need to find this distance, and I need to find this height. And if I know that, well, I know that my circle, given my radius, is differentiable and continuous at this point. So this tangent line is from the derivative of whatever function you had prior, right? So you can just call that limit as x approaches your x. Yeah, limit as x approaches x from f of x from the negative side. So, and that will be your derivative because we're looking at the tangent line, right? So you'll notice that this perpendicular line here will be your f prime of x right here. It'll be -1 over f prime of x. Because if that's your slope here, well, your slope here has to be the opposite reciprocal, right? So if we know that, well, we have a point, we have a slope, well, guess what? Point slope form, right? So then we have this point. I'm just gonna call it a comma, let's just call it a comma b, right? And we can just plug this into a slope equation. So we'll do y minus b, which is your b that you got here, because, well, yeah, we don't know b yet, right? So this will still be a variable, is equal to -1 over f prime of x, right? Which is your slope of this line here, right? And you have x minus a, which you also don't know. Or in fact, we do know our b, my bad. You know that b is 0 because we're trying to find out what x that's b is. Because if we know this distance as well, we have to know this distance to know how much we need to move it, the center of the circle. Because when you're translating a circle, you're translating in terms of the center of the circle, right? You're not moving it in terms of this point. So you can't just say, I'm gonna move x minus this x. No, you have to say x minus the center of the circle. And that's where it gets complicated, right? So what you'll do is you'll set this b equal to 0 so that your y is 0. And you have y minus 0 is equal to -1 f prime of x minus a. And since we know this point, right, well, we can just plug that in, right? Y and x. So you have f of x is equal to, and I'm talking about this f of x with respect to where you're connecting it. And you can find that using your previous equation and just plugging it in, right? So you have f of x is equal to -1 over f prime of x. And then your x will it'll be also x here, right? So that's fine. That'll also connect. And then you'll have x minus a. So we know x, we know your slope, we know this f of x, we just need to find where a is. So what you'll do is you can distribute that slope, right? F of x is equal to -1 over f prime of x times x minus a over f prime of x. I'm just distributing here. And you'll get a over f prime of x is equivalent to f of x plus x over f prime of x. And then you can just multiply everything by f prime of x. And you'll get a is equal to f of x times f prime of x plus x, because the primes cancel out here, right? So now we know that A, we know B, we know X, we know f of X, we know this point, right? And we know what our slope is on here. So knowing that, we can call this distance, like I have all these points, right? I'm just trying to find out how much I need to move my circle to move from here, this distance, and up here. I just need to move my circle. That's all I'm doing. Because I know that my slope has to connect here if these things are true. So I'm just trying to find out this distance, this distance. That's the whole gist of this, if you're kind of lost on what I'm trying to do. So this distance here will be x minus a, right? And this distance here, which I labeled earlier, is a, right? So I already know I need to move it that much. And if you'll notice, hey, this point is really just f of x, right? So this distance here, this height, is f of x. So I can do Pythagorean theorem. I'm gonna just label this as my slope of m. So if I do Pythagorean theorem here, you'll notice that this distance of this hypotenuse is the square root of x minus a squared plus f of x squared, right? So now that I know that distance, I can do what I was saying earlier about similar triangles. So this radius, or here, let me explain it this way. This and this bottom length have to be proportional to the full length and this bottom length here, right? So if I do that, I can just say, I move this all over, I can say that my hypotenuse, which is the distance of the square root of x minus a squared plus f of x squared over my bottom portion, which is x minus a in this situation, is equivalent, because they're similar triangles, to this plus r. So I'll have this, oh, it went inside the page. There we go. You'll have that distance plus r, your radius, right? And that's your full length, right? I'm comparing this triangle to this large one here, right? Because these two are similar triangles. So the full length of that is the hypotenuse plus r, and then plus this unknown height. Or actually, I'm doing it for the length. So in reality, oh, we actually don't know this length, actually. Oh, wait, that's fine that we don't know it. We're going to find it. Okay, that's fine. So I'm going to call this full length. Let's just call it, z. Z. So I'm going to say that that should be proportional to z, right? And now I just solve for z. So solving for z, I'm going to delete these lines here. If I solve for z, I get z is equal to, if I move that over, right, and I'm going to subtract this down, divide it down, and then multiply this up. So you'll catch what I'm doing. I'm going to multiply the x minus I to the top, and I'll have to multiply that by the whole thing, the plus r as well. So I'll have square root of x minus a squared plus f of x squared, the root of that, plus r. So that's multiplied over. I'm going to multiply my z over and then divide by this. So that'll be So that'll simply be this whole thing. Oh my lord. That'll be that whole thing, but on the bottom. Right? So I know z. I know this full length. Now I just need this length here. So what I can do is I'll set Pythagorean theorem again, because I know that this is a right triangle, right? I have z, I have my total length, so just Pythagorean theorem all over again. So I'm gonna move down a bit, because we're gonna need to do this portion squared, this squared, and square root of that, and then z squared, and then this is also gonna be squared. So it's gonna be big and messy. So what we're gonna do is, yeah, we have to do this length, because this is my hypotenuse, right? We have the square root of x minus a squared plus f of x squared plus r, which is my hypotenuse. So if my hypotenuse is equal to my bottom length squared, right, is equal to z squared plus my height, which I'm just going to call this whole yellow thing h. So that'll be h squared. So h is equal to this whole thing squared, yeah, and then minus, is it? Yeah, it's minus z squared, because I'm moving the z over to the side. So minus z squared. And then since I take the square root of h, guess what? I have to take the square root of this whole thing. So now that I know my h, well, I know h, I know z, I know a. So knowing that, well, now all I have to do is just know that if I have my circle over here, right? I'm gonna draw it in a different color. If I have my circle here with my thingy here, I know that, oh my gosh, I know that this point, if I know this and I know my radius, well, whatever this is here, I just need to move it over a, like this starting length a, plus c, and then I need to move it up h, right? So my circle equation, which was originally x minus, remember your number n, plus x minus y, and remember these are squared, right? Circle equation is, nope, I made the same mistake twice. Y minus m is equal to your radius squared. So your equation will just be x minus how much you're moving it horizontally, so a plus z squared plus y minus h squared, and your h is just your height, and that's all equal to r squared. So this y is a variable that stays like that in your equation. This x is a variable that stays like that in your equation. And yeah, you know the rest. You know z, you know h, you know everything. So it's quite interesting because everything is interdependent of each other, and eventually r comes into the equation. So since I did it like this, well, you can plug in any r and it'll still work for you. So I guess pick an r that, you know, makes sense and won't make your whole thing look stupid, something like this, because that would be funny, right? Doing it this way, you can kind of just pick a nice radius, whatever you want, and then it'll tell you how much you need to move it to make it good.